Welcome to COMSOL tutorial on solving linear and non-linear equations. So in the last tutorial we have covered general introduction. Today we're going to solve some examples for linear and non-linear equations, and as I have pointed here, these are the building blocks for numerical analysis, and Dr. Kumar has already discussed various algorithms in his lectures for solving these linear and non-linear equations. He has covered direct methods like Gaussian elimination, LU decomposition. He has also discussed iterative methods, Jacobi's successive over relaxation and Gauss-Seidel, etc. So all these algorithms which are discussed in class will be useful to us in selecting different options available to us in COMSOL. So in this short tutorial I will show you how to set up and solve these linear and non-linear system of equations. Probably you may not be using COMSOL just for solving these equations, but these equations could be a part of your a larger model. So for example, in the later ALE tutorials you will see that we combine these equations with other PDEs to solve for particle displacement and particle velocity. So let's start our tutorial on solving linear and nonlinear equations in COMSOL. So the first example is the how to solve a simple system of linear equations. So we have four equations here, and we have four unknowns. So again, let's start with this COMSOL. If you start, you'll get this screen, and because there is no space dependency, it's a zero dimension problem. I select 0D and click on the next arrow, and I have recently used this. So we are solving for simple ODEs or algebraic equation. We need to use this interface, global ODE and DAE. So you can select it through, if you click mathematics, go to this ODE and DAE interfaces, click this and add to this selected physics, then click next, and then you can select what kind of study you want to carry out. So I'll select stationary and then finish. Okay, so if I just go back here on this, so I have written here these equations need to be entered in the form of fx is equal to 0. So we need to take this right hand side to the left hand side. So this first equation will contain the term minus 6. So let us just enter this equation, 10x minus 7y. So in this global equations, if you click this, you can see this settings, this table, and so the first column here is the name for the state variable. So for example, it is say x, and then in the second you have to write the function expression, and it should be equal to 0. So if our expression for this say 10x minus 7y, so let me enter it, 10 times x minus 7 times y, and 3z 5u 6. Okay, so it will be 3 times z plus 5 times u, and taking 6 to the left hand side will be minus 6 is equal to 0. So we have written the first equation, state variable x. Similarly, we need to write declare other state variables y, z and u, and similarly we need to write these equations. So I'm just gonna import it. I have saved them before, so I'm just gonna delete this and open this already saved system of equations. So I open it, and so if I just resize this, so you can see we have x, y, z and u as our variables, and then we have entered all the 4 equations shown in the slide here. So that's how we need to enter the linear system of equations. And with this and with default solver settings, you can just right click and say compute. And you can always look at the log, its linear solver in the result section. If you click, you can just go to the derived values and click on the state variable x, and you can evaluate in a table. So x is 5. If you go to y and evaluate in the same table, y value is 4. Similarly z and u. So it is the very simple example which we have solved, and the answer is same what is written in this slide also. So again, as I mentioned to you, you're probably not going to use COMSOL just for solving such simpler system of equations. So let's move on to our next example, which is, before that we have this schematic showing Newton-Raphson method. So I'm going to skip this because it's being covered in the lecture part. So just to point this out, that the next correction is estimated using this formula shown here. Okay, so now in this slide I have shown the COMSOL algorithm for solving nonlinear equation. COMSOL utilizes damped Newton method. So Newton method, using the following the formula on the following slide, it calculates this predictor x1 correction using this predictor delta x, which is based on the Jacobian, but this the damped Newton method, it multiplies this correction with a damping factor lambda, which is shown here, and this lambda value varies between 0 to 1. So depending upon your choice of initial guess, the algorithm calculates lambda such that the function value is less than the previous iteration. So more details you can find it in the advanced solver topics in COMSOL documentation. So but the schematic is shown here for the damped Newton method. Okay, so let's do a quick quadratic equation example in COMSOL. So if I go back here and using the same interface for ODE or used for solving algebraic or non-linear algebraic equation, so I'll just going to delete these 3 variables, and for x I'm going to modify my equation. Say we know the roots of the equation as 2 and 4, then my quadratic equation will become x squared minus 6x plus 8 is equal to 0. So this equation we know has roots at x is equal to 2 and x is equal to 4. Now for this nonlinear equation we need to give an initial guess or initial value, and this value will determine the solution, whether we're going to converge at x is equal to 2 or x is equal to 4. So let me choose a value of 5 here and just say compute. If you compute and go to a state variable x and evaluate in a new table, the solver has converged to root 4. Now if I go back to my equation and change my initial guess to say 1, now it is more closer to the value root 2. So if I select this, I'll just again compute the same quadratic equation, and if I evaluate it in the same table, now it has converged to root 2, and we can check this log here. So right now for these two initial guesses, it has the COMSOL algorithm has used a damping factor of 1. So when it is using a damping factor of 1, it is your Newton method. It is with damping factor equal to 1. So now if I choose say if I choose a gas of 3, and if I now compute the solution, there is error, failed to find the solution. And if you look at the error, say system matrix is 0, and if you carefully look at this equation, x is equal to 3, initially x is equal to 3 is your stationary point where your derivative your slope is 0 basically. So the correction, the Newton method cannot find the correction because the slope, your slope is parallel to the x-axis, so it's a stationary point. But if we can change our guess little bit, say from 3 to 3.01, and then compute, then you can see that it is able to find, but now it took roughly 5 iterations, and with initial 2 iterations are with damping factors, small values of damping factors of 0.01 and 0.1. So because our initial guess was close to stationary point, the correction, the regular Newton method produces overshoot, and which needs to be damped using this damping factor values. And that's how COMSOL solved this simple equation. So with this gas of initial gas of 3.01, if we again just look at the converge root, so with that gas it has converted to a value of 4. So we have seen this simple quadratic equation, and we have learned these points which I have mentioned here. Okay, let's move on to the next slide. Okay, so another example I have for nonlinear equation is this van der Waals equations. For say we can if we given you these parameters, then we want to calculate V using this nonlinear equation. V is a specific volume in this case. So let us quickly write this equation and solve this equation in COMSOL. So again, so for all these parameters we can just defining these A, B, R is the gas constant, T is temperature. So I can just right click this global definition and select parameters. In this parameters I can enter all the model parameters. For example, say P is equals to 1, and you can enter in it in any units. So we're going to see different unit types in the next tutorials, but similarly you can enter all the variables, but I have already saved that file earlier, so I'm going to load it from a file. So I open this and click on this van der Waals equations parameter. I open it, and so because we have already defined P, so I'm just going to delete this P. So now we have all the variables, all the parameters defined for solving this. And So this V naught is the RT over P, which is the calculation of the specific volume using ideal Gauss law. PV is equal to RT. So let me now just add this equation. So let me call the state variable as V, and let me enter the van der Waals equation here. So the first term is P plus A over our unknown variable V square multiplied by V minus B, and it is equal to RT, but since we need to write equation as fx is equal to 0, so I'll take this RT term to the left hand side with the negative sign, R times T, which is equal to 0, and in the initial value I'll give my V naught, the specific volume calculated from ideal gas law, as my initial gas. Okay, so it was very simple. Just we need to enter the nonlinear equation fx is equal to 0 in this form, and let us just let me quickly delete the solver configuration, delete solver, so that it will clear up all these old derived values. Now again, just say compute failed to evaluate expression. Okay, so let's see what this error is. So it is saying failed to evaluate variable P. So let us go back. I think we have defined P. Okay, so there is somehow this P is omitted from this list, so let me define it P as, I think it was 20. Let me cross check quickly. Okay, means we can use any value. So if it is 20, so let me just write it as 1, and with this compute this. So again, you can look at the log, and state variable V, you can just look at the table and see the value is 28.71. so this is the specific volume estimated using van der Waals equation. And if you look at the V naught value, it is also close, because the pressure is, we are calculating at just 1 atm, so the two equations give similar numbers. So similarly we can carry out the same computation with different pressures. So I think the next we are talking about continuation method. So say in this example I want to estimate my specific volume at different pressures, say ranging from 1 atm to 100 atm. Then one way is to use Newton method for every value of P, or other option is we can define our problem like this, where this is your equation in terms of parameter lambda, or in our, if we consider the example for van der Waals equation, our parameter is P and our variable is V, specific volume. So the continuation method is use your initial solution, like say for parameter P naught, or in this figure for parameter lambda naught, if you have initial solution U naught, then the same solution is used as initial guess for solving for the next parameter value. So if I want to talk about in terms of our example, then say if we have solution at P is equal to 1 atm for specific volume V, then that solution is used as an initial guess to solve for the next parameter value, say pressure is equal to 280 m. So this is what this schematic figure shows, and these algorithms are also discussed in lecture, continuation, Euler continuation method. So this is the one method where you use the previous solution as initial gas. The next method is shown here, where you use a tangent to the initial solution as your initial gas. So this is also covered in lecture, so I'm going to skip this here. Just I would like to show you the COMSOL implementation part for this. So say if P is your parameter and you want to calculate various solution for different values of P, so just need to go to this tab, stationary studies tab, and in the extension you can select continuation. Okay, so and now you need to define with respect to which parameter, which is your continuation parameter. So if you click add, then you can select this from the list of parameters that we defined here in the global definition parameters tab. So if I select P and click OK, then I can give a parameter value range here. So if I click this and say start from 1, stop at say 200, and with the step of 1, and just add this. So now it's going to calculate the same state variable for this range. And now if you open this tab, so along with your direct solver there is an additional parametric solver tab, and if you look at the predictor here, so this predictor is what kind of initial gas you are providing. So we have discussed two. So constant means you are using the previous solution, and if you select linear, it means you are using the tangent to the in previous solution as an initial gas to the next parameter value. So this is essentially the same thing which we have discussed in the slide and also discussed by Dr. Kumar in the lecture. So it is usually by default it is automatic here, and which is pretty good, and most of these default choices are really good in COMSOL, so you don't need to change this. So let us just quickly solve this. So we have specified our parameter range, and we have seen the parametric solver options. So let us just say compute. If I look at the log, so it has finished computing for all these 200 parameters. And so if I go to this state variable v2, now we can import this data for V for all the parameters, or you can select it from a list for which value you want to see the data. And then if I just select all and evaluate my variable in a new table, you will get a new table which has the solution for all the parameter values. Okay, and you can just use this plot function to see the graph, how your volume is changing with the parameter P, which is the pressure in this case. So let me see what else is here. So arc length continuation, so this part I'm going to cover in the next tutorial. So arc length continuation is another kind of continuation where this regular Euler Newtonian continuation fails. For example, the continuation algorithm that we discussed cannot trace the solution which has these turning points like this. So we'll come back to arc length continuation in our next tutorial. So just to summarize, today we have seen how to solve a set of linear equation, how to solve non-linear equations, how to do how to implement continuation, for solving equation. And similarly, say if you have a system of nonlinear equations, say more than one nonlinear equation, then you can use the similar interface global equations to solve for the system of nonlinear equations. So again, if you have any questions, please feel free to contact me, and with this I'll end this tutorial on solving linear and nonlinear equations in COMSOL. Thank you.